Hi everyone, welcome to this detailed walkthrough of the OCR A-Level Chemistry Paper 1 of June 2018. Specification-wise, there is not much of significant difference in the chemistry content taught across OCR, AQA and EdExcel exam boards, and therefore I would strongly recommend A-Level chemistry candidates to work across all past papers to gain significant mastery over the chemistry concepts. This paper is for 100 marks and is for 2 hours 15 minutes duration, and in this walkthrough we will try to work within the time allocated. Let us now get to the questions. Question 1. A sample of boron contains the isotopes B10 and B11. The relative atomic mass of boron sample is 10.8. What is the percentage of B11 atoms in the sample of boron? Since we need to find the percentage of B11 atoms, let us assume that B11 atoms percentage is X percentage. So let's write let B11 be X percentage in the sample. Therefore, B10 would be 100 minus X percentage. Therefore, the relative atomic mass calculation of the sample will go like this: X times 11 plus 100 minus X times 10 all over 100 is equal to 10.8. Expanding this, we get 11x plus 1000 minus 10x is equal to 100 times 10.8 is 1080. That makes it quite simple now for us. 11x minus 10x is 1x is equal to 1080 minus 1000 is 80, which leads to x is 80%, and that is C. Question 2. In the compound ICl2 positive SbCl6 minus, the oxidation number of chlorine is -1. What are the oxidation numbers of iodine and antimony in the compound? In the cation part, that is ICl2 positive, ICl2 positive, we have been told that chlorine has got an oxidation number of -1. Therefore, this is -1 times 2 minus 2. That has been balanced by iodine, and there is a positive charge over there, which means iodine should have an oxidation number of +3. Keep it over there. And let's look at the anion part. That is SbCl6 resulting in a single minus over there. This Cl6 means 6 times -1 is equal to -6. That has been balanced by Sb, and still there is a minus sign over there, which means Sb should be 1 short of 6, that is +5. Now let's look at the option which gives us +3 and +5. No, +3 and +5, that is C, correct. So this is C. Question 3. What is the number of hydrogen atoms in 0.125 moles of C2H5OH? We know that the number of molecules / ions / atoms in 1 mole of any species is the Avogadro number, which is 6.02 times 10 to the power of 23. Therefore, in 0.125 moles of C2H5OH, the number of molecules will be this multiplied by 0.125. Not over yet. The question is asking us the number of hydrogen atoms. Therefore, in 1 molecule of C2H5OH, there are 5 plus 1, 6 hydrogen atoms. Therefore, in this many molecules, there will be 6 times of that as hydrogen atoms. So let's write N hydrogen atoms is equal to this. Putting into the calculator, we get this as 4.515 times 10 to the power of 23. Looking at the options here, 4.1515 times 10 to the power of 23 is B. Question 4. A student titrates a standard solution of barium hydroxide BaOH twice with nitric acid HNO3. 25 cubic centimeters of 0.0450 moles per dm cubed BaOH twice are needed to neutralize 23.35 cubic centimeters of HNO3 aqueous. what is the concentration in moles per dm cubed of the nitric acid? This is a very common quantitative chemistry question from GCSE to AS level to A level. If we write the equation for the neutralization reaction, it will be easy for us to understand and solve this question. In any neutralization reaction, the base reacts with an acid to form a salt and water. Here the salt will be BaNO3 twice plus H2O. We will balance the equation later. So this is the equation. So BaOH twice plus HNO3 gives BaNO3 twice plus H2O. So looking at this, we need 2 parts of nitrate here. So if I put 2 here, then we also need 2 molecules of water. Therefore it becomes 2H2 here. In titration questions, there will be 4 aspects, of which 3 will be given to us, and we have to figure out the 4th missing one. The 4 aspects are the concentration and volume of the base and the concentration and volume of the acid. So let's write whatever is known to us here. BaOH twice, volume is 25 cubic centimeters. So 25 cubic centimeters can be converted into dm cubed. So 0.025 dm cubed, that's the volume. And its concentration 0.0450 moles per dm cubed. And in the case of nitric acid, it requires a volume of 23.35 cubic centimeters, which is 0.02335 dm cubed. And its concentration, that's the one is missing. Let us first figure out how many moles of barium hydroxide are there in this volume with this concentration. So going by the NVC triangle rule, we can say number of moles of barium hydroxide is equal to the volume times the concentration, that is 0.025 times 0.0450, and that gives us 1.125 times 10 to the power of minus 3 moles. Okay. Now let's look at the equation once again. 1 mole of barium hydroxide reacts with the 2 moles of nitric acid. Therefore, the number of moles of nitric acid that is taking part in this complete reaction is 2 times of 1.25 times 10 to the power of minus 3. Now the last bit. Concentration of nitric acid, which what we are after, is just the number of moles divided by the volume. Therefore we can write concentration of HNO3 is equal to 1.125 times 10 to the power of minus 3 times 2 divided by its volume, which is 0.02335, which gives us in the calculator 0.09635 etc. D gives us the correct option, therefore the correct answer is D. Question 5. Which statement best explains why nitrogen has a larger first ionization energy than oxygen? Before we get into the options, it would be better to look at the electronic configurations of both nitrogen and oxygen. You know, nitrogen has got an atomic number of 7 and oxygen has got an atomic number of 8. Therefore, the configuration of nitrogen goes like this: 1s2, 2s2, 2p3. And that of oxygen goes like this: 1s2, 2s2, 2p4. From this you can see that there are 4 electrons in the p orbital for oxygen. If you draw the 3 boxes for the p orbital for oxygen, the first electron fills in the first box, second one, third one, and the fourth one comes and sits in the first one alongside the already existing electron. Therefore, there is going to be a significant repulsion between them because they both have the same energy and they have the same charge of -1 each. That repulsion force makes it easy for one electron to be knocked out of the oxygen atom. That is the first ionization energy. This is not the case with nitrogen because the 3 boxes are filled with 1 electron each and there is no repulsion between them. The correct statement would be there will be less repulsion between them than in oxygen. Now let's look at the options. Nitrogen atoms have less repulsion between p orbital electrons than oxygen atoms. That's correct. Let's look at the others also. Nitrogen atoms have a smaller nuclear charge than oxygen atoms. That is actually true. Oxygen has got a higher nuclear charge than the nitrogen, but that's not the argument here. If nitrogen has got a small or smaller nuclear charge than oxygen atoms, then the argument should be that the first ionization energy for nitrogen should be less, but that's not the argument here. Nitrogen atoms have higher first ionization energy, therefore this is not relevant. Nitrogen atoms lose an electron from this 2s subshell, not correct. Nitrogen atoms have an odd number of electrons while oxygen atoms have an even number, not relevant. So A is the correct option here. Question 6. In the periodic table, element X is in group 2 and element Y is in group 5. What's the likely formula of an ionic compound of X and Y? If an element is in group 2, its ion will be having a charge of +2. Therefore, ion of X will be having X plus 2 charge. So let's write that as X with a positive 2 charge. Okay. And when an element is in group 5, its ion will be having a charge of -3. That means Y will be having a charge of -3. Let me put this +2 outside here. Therefore, as a rule of thumb, X will be joining with 2 atoms of Y and Y will be joining with 3 atoms of X. Therefore, the compound formed will be X3, Y2. And looking at the options here, no, no, yes. So it is C. Okay. If you want to look at an example to demonstrate this, look for aluminum and oxygen. Aluminum has got a charge of +3 for its ion and oxygen has got a charge of -2 for its ion. Therefore, the compound formed will be Al2O3. Question 7. Which statement about ammonium carbonate is not correct? Therefore, in this question, 3 of the options will be correct statements and only 1 will be an incorrect statement. Let us look at each of the options. It reacts with the barium nitrate aqueous to form a white precipitate. That's correct, because when ammonium carbonate reacts with the barium nitrate, one of the products formed is barium carbonate, which is a white precipitate because it's insoluble in water. So that's the correct statement. Second, it effervesces with dilute nitric acid. That's also correct, because when ammonium carbonate reacts with any acid, it will release carbon dioxide, which is a gas, and it will definitely effervesce. It releases an alkaline gas with warm NaOH aqueous. That's also correct, because the alkaline gas formed in this reaction will be NH3. Finally, it has the formula NH4CO3. That's incorrect, because carbonate has got an oxidation state of -2. Therefore, the compound formed will be NH4 twice CO3. That's the correct formula for the compound. Therefore, the answer is D. Question 8. A reaction is first order with respect to a reactant X. Which rate concentration graph for the reactant X is the correct shape? So if I label this y-axis as rate and x-axis as the concentration, you can see that the rate is proportional to the concentration. When concentration increases, the rate also increases in a 1-to-1 scale factor proportion. Therefore, this answer is correct with respect to reactant X. Option B. You can see this diagram. If I mark this as rate and this as concentration, it shows that the rate comes down as the concentration increases which is not a correct option in a reaction. Therefore, this is an incorrect diagram at all. What could happen is, if I mark this as a concentration time graph, this is concentration over the y-axis and time over the x-axis, then it could be a relevant diagram where the concentration decreases, concentration of the reactant decreases when the time increases. That means it is a concentration time graph showing zero order reaction with respect to a particular constant, a reactant. Looking at option C, you can see that if I label this as rate and this as concentration, then the rate remains constant regardless of the increase in the concentration. Therefore, this is a zero order reaction with respect to that reactant. So that is also not a correct option for us. And then D, if I mark this as R and this as concentration, it shows that the rate increases at varying rates as the concentration increases. This is applicable for a second order reaction. So all in all, the correct option for us is A. Question 9. The reversible reaction of sulfur dioxide and oxygen to form sulfur trioxide is shown below. So the equation is given. You can see from the equation that all the reactants and the product are in gaseous state. An equilibrium mixture contains 2.4 moles sulfur dioxide, 1.2 moles oxygen and 0.4 moles sulfur trioxide. The total pressure is 250 atmospheres. What is the partial pressure of sulfur trioxide? Well, the partial pressure of any gaseous species at equilibrium is equal to its mole fraction times the total pressure. Let us first figure out the mole fraction of sulfur trioxide. That's equal to the number of moles of sulfur trioxide at equilibrium, which is what, 0.4 moles, upon the total number of moles in the mixture, that is 2.4 moles plus 1.2 plus 0.4, and that's equal to 0.4 divided by 4. Therefore, partial pressure of sulfur trioxide will be its mole fraction, which is 0.4 over 4, times the total pressure, which is 250 atmospheres, and that gives us 1/10 of 250, which is 25 atmospheres. Looking into the options, A is not correct, B is correct. Therefore, the correct option for us is B. Question 10. A buffer solution is prepared by mixing 200 cubic centimeters of 2 moles per dm cubed propanoic acid with 600 cubic centimeters of 1 mole per dm cubed sodium propanoate. Ka for the propanoic acid is given. What is the pH of the buffer solution? So think about the strategy for this question by going backwards from the end point. So we need to find the pH of the buffer solution. Therefore, we will calculate the hydrogen ion concentration. That can be calculated from the Ka equation. The Ka equation goes like this. Ka equals hydrogen ion concentration times the salt ion concentration divided by the concentration of the acid, which we can write as Ha. To find the concentration of each of these species, we need to know its number of moles and the total volume. So starting from propanoic acid, let's write N of Ha is equal to its number of cubic centimeters, that is 200 cubic centimeters, that is volume, times the concentration, which is equal to, let's write in dm cubed, 0.200 times 2 is equal to 0.4 moles. Right. Therefore, the concentration of the acid will be equal to 0.4 moles divided by the volume. Here, a common student error is just taking the 200 cubic centimeters once again, which is incorrect. We need to look at the total volume of the solution, which is 200 plus 600. Therefore, it is 0.8 dm cubed, which gives us 0.5 moles per dm cubed concentration of the acid. Similarly, let's calculate the concentration of the salt solution, which is sodium propanoate. So it has got, let's say, A minus here, that is equal to its volume times its concentration, which is 0.6 times 1, which is equal to 0.6 moles, which leads to the concentration of the salt solution equal to number of moles divided by the total volume now is 0.8, which gives us 0.75 moles per dm cubed. So we have all the information that we need: concentration of the acid, concentration of the salt solution. Putting this into the Ka equation, we get 1.32 times 10 to the power of minus 5 equals hydrogen ion concentration, which is what we are after, times the salt solution concentration is this 0.75 whole divided by the acid concentration is 0.5. Okay, rearranging this, we get hydrogen ion concentration is equal to 1.32 times 10 to the power of minus 5 times 0.5 whole divided by 0.75. That gives us 8.8 times 10 to the power of minus 6 moles per dm cubed. Once we get the hydrogen ion concentration, pH is equal to minus log to the base 10 of hydrogen ion concentration, which putting into the calculator we get 5.055. Right, now let's look at the options given here. 4.58 no, 4.70 no, 5.06 is correct. So let's mark the answer C. Question 11. The table below shows standard entropies. So substance CO gaseous, hydrogen gaseous, methanol liquid are given. What is the entropy change delta S in joules per mole per Kelvin for the following reaction: CO gaseous plus 2H2 gaseous giving CH3OH liquid? So delta S, the entropy change, is the total entropy of all the products minus the total entropy of all the reactants. So let's write delta S is equal to the total entropy of all the products 239.7 minus the sum of the entropy of all the reactants. Also consider the number of moles there. So 197.6 plus 2 times 130.6, which when we put into the calculator we get minus 219.1, and going by the options it is A. Question 12. The redox equilibria for a hydrogen-oxygen fuel cell in alkaline solution are shown below. So two equations are given with the electrode potentials. Please note the first equation has got electrode potential more negative than the second equation. Question: what is the equation for the overall cell reaction? Okay, so in this question, instead of going through the options A, B, C, D and figuring out which overall equation is the correct one, it's better to work out the overall equation from the available information ourselves and then compare. So this equation has got an electrode potential more negative than the second equation. Therefore, we need to write the first equation as a half equation by reversing it and showing it as an oxidation reaction. Currently, it is a reduction reaction. So rewriting the first half equation, H2 gaseous plus 2OH minus aqueous gives 2H2O liquid plus 2 electrons. Now writing the second equation, half O2 gaseous plus H2O liquid plus 2 electrons gives 2OH minus aqueous. Now add the left hand side of both the equations and add the right hand side of the both equations and put them in one equation. For example, we write this as H2 gaseous plus 2OH minus aqueous plus half O2 gaseous plus H2O liquid plus 2 electrons gives, on the other side, 2H2O liquid plus 2 electrons plus 2OH minus aqueous. Now cancel out things which are identical on both sides. So there is 2OH minus here and 2OH minus here. We can cancel them. We have got 1 H2O cancels against 1 H2O from here. Both the electrons go away from both sides. So finally we have got the overall equation, which is H2 gaseous plus half O2 gaseous gives, on the other side we have got H2O liquid. And going by the options here, no, 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 and it is D. Question 13. Which enthalpy changes are endothermic? So there are three statements given. Let's review each of them. The first one is the bond enthalpy of the CH bond. This is endothermic because we need to give energy to break a bond. In fact, the definition of the bond enthalpy itself is the amount of energy required to break 1 mole of a specific bond in a gaseous molecule. Therefore, this is endothermic. Statement 2. The second electron affinity of oxygen. This is also endothermic. We are talking about the second electron affinity because the oxygen has already become an ion with 1 negative charge. Now imagine we are trying to add 1 more electron to it. It would require more energy because there is a repulsive force between them and that has to be overcome. Hence this is also endothermic. Third, the standard enthalpy of formation of magnesium. This is not endothermic because as per the definition, the enthalpy change of formation of any element is 0. Magnesium is an element and therefore there is no enthalpy change of formation. So that is classified as 0. So we can say it is not endothermic. So we should have 1 and 2 as the correct answer. So only 1 and 2 is B. Question 14. Which statements explain why reaction rates increase as temperature increases? Statement 1. The activation energy is less. That's not the reason, because when the temperature increases, activation energy required for a reaction does not change. It remains the same. It's only the number of molecules that have the required activation energy that changes, and therefore this is not the case. Second statement, collisions between molecules are more frequent. That's correct. When temperature increases, the collisions between molecules become more frequent because they acquire more energy. That's correct. Third one, a greater proportion of molecules have energy greater than the activation energy. That's also correct. When the temperature increases, more molecules acquire energy levels that are equal to the activation energy. Therefore, options containing 2 and 3 are the correct one. So C. Mark C. Question 15. Which statements are correct for the complex PTNH3 twice Cl2? One of its stereoisomers is used as an anti-cancer drug. This is a coordination complex compound by name diamine dichloroplatinum. Note the double M here, that is to differentiate it from the amines in organic compounds. This compound has got two geometric isomers. One is called the cisplatin and another is transplatin. If you draw the shape of this, as the name cis indicates, you draw platinum here, Cl, Cl, NH3, NH3. This cisplatin is a very famous anti-cancer drug. Therefore, option 1 is correct. Now let us look at the second statement. It has bond angles of 109.5 degrees. This is not true in the case of this compound because it is square planar in shape. Remember that to get an ideal bond angle of 109.5 degrees, the molecule should be tetrahedral in shape with 0 lone pair of electrons. In the case of the ammonia molecules in this compound, each ammonia molecule has got this nitrogen having 3 bonds with hydrogen atoms, and the lone pair has been donated to the platinum as a dative covalent bond. Therefore, strictly speaking, there is no lone pair available here. Therefore, it might mislead you to think that the bond angle is 109.5 degrees. Therefore, for the purpose of A-level chemistry, please memorize that if it is platinum with 4 ligands, it will end up as a square planar shape and not a tetrahedral shape. Other example is platinum Cl4 2-. This is also square planar. So let me write here square planar. As a contrast, please memorize that CuCl4 2- or cobalt CuCl4 2- are tetrahedral in shape. The reason for this exception is due to platinum, and that is beyond the OCR A-level chemistry specification. We will be learning that when you go to undergraduate course in chemistry. Statement 3. It has optical isomers. That is not true. To have optical isomerism, there should be 4 different groups attached to the central atom. Here, there are 2 ammonia molecules attached to platinum and 2 chlorine attached to the platinum atom. Therefore, it can't show optical isomerism. That's also not true. So, in short, this compound shows geometrical isomerism but does not show optical isomerism. Therefore, let's look at the options here. Only one, that is D. Question 16. This question is about enthalpy changes. Table 16.1 shows enthalpy changes that can be used to determine the enthalpy change of hydration of fluoride ions. So the table gives the enthalpy change of hydration of calcium ions, solution of calcium fluoride, and lattice enthalpy of calcium fluoride. Question. Explain what's meant by the term enthalpy change of hydration. I would strongly recommend chemistry students to study in detail the definition of various enthalpy changes. There's quite a lot of them: enthalpy change of formation, neutralization, combustion, hydration, solution, etc. There is no chance of getting good marks in A levels without knowing these. Talking about enthalpy change of hydration, consider gaseous ions. For example, Ca2 positive gaseous plus 2 fluoride ions gaseous. When they undergo hydration, what it means is the enthalpy of hydration is delta H hydration. They become aqueous ions, Ca2 positive aqueous plus 2 fluoride aqueous. Now consider these gaseous ions becoming a lattice, that is calcium fluoride solid lattice. This is called enthalpy of lattice, or let's say lattice enthalpy. Now consider this calcium fluoride lattice dissolving in water to form an infinitely dilute solution containing calcium and fluoride ions. That's called delta H solution of calcium fluoride. So enthalpy change of hydration is the energy change when 1 mole of gaseous ions dissolve in water to form aqueous ions. Part 2. The enthalpy change of hydration of fluoride ions can be determined using the enthalpy changes in table 16.1 and the incomplete energy cycle below. On the dotted lines, add the species present, including state symbols. We can start from the top, that is the highest energy level, using the gaseous ions. So we will write here Ca2 positive gaseous plus 2 fluoride gaseous. In the next stage, we will write one of these gaseous ions becoming aqueous ions. So let's say Ca2 positive becomes aqueous ions, and fluoride ions continue to be gaseous ions. So here we have been given that the enthalpy of hydration of calcium 2 positive is minus 1609. In the next stage, we will write fluoride ions also becoming aqueous. So Ca2 positive aqueous plus fluoride aqueous ions. But here this value is not given to us. We have to find it out. Since there are 2 fluoride ions, let's make it 2 fluoride here, 2 fluoride here, and this is 2 times of that. On the left hand side is this lattice enthalpy, that is the energy given out when the gaseous ions become a solid lattice. So we will write here CaF2 solid, and this is given to be minus 2630 kilojoules. This arrow represents the enthalpy of solution, that is when calcium fluoride lattice dissolves and becomes infinitely diluted in water. Therefore this is plus 13. These enthalpy numbers are not required to be written in this question here. We were only asked to fill up these dotted lines, but these enthalpy numbers will be useful for the next part of the question. Part 3. Calculate the enthalpy change of hydration of fluoride ions. Looking at this energy cycle diagram once again, you can see that this enthalpy of hydration right up to this, let's write enthalpy of hydration of calcium and fluoride ions is actually the net of the lattice enthalpy and the enthalpy of solution. So we could write minus 2630 plus 13 is equal to minus 1609 plus 2 times the delta H hydration of fluoride. Writing the equation here, minus 2630 plus 13 is equal to minus 1609 plus 2 times delta H hydration of fluoride ions. Therefore, simplifying this, minus 2617, which is the net of these, plus 1609 should be equal to 2 times delta H hydration of fluoride. Therefore, delta H hydration of fluoride ions will be equal to minus 2617 plus 1609 whole divided by 2, and putting this into the calculator we get minus 504 kilojoules per mole. Part 4. Predict how the enthalpy changes of hydration of fluoride ions and chloride ions would differ. Explain your answer. Firstly, let us write delta H hydration of fluoride ions will be more negative or more exothermic than the delta H hydration of chloride ions. Now we will write the reasoning here. From the periodic table, you can see that fluorine is in period 2 and chlorine is in period 3, which has got one more shell of electrons, and therefore fluorine is smaller than chlorine. Similarly, fluoride ion is also smaller than chloride ion, and they both have the same charge, which leads to fluoride having higher charge density than the chloride ion. Now the higher charge density of fluoride ions leads to greater attraction to water molecules. And if you look at the chemistry of bond formation, you will see that when bonds are formed, energy is released. And when stronger bonds are formed, significantly more energy will be released. So we will write here, this is because fluoride ions are smaller in size than chloride ions, at the same time having the same charge, but having same charge. Leading to higher charge density and greater attraction to water molecules. Part B. Fluorine reacts with steam as shown in the equation below. So the chemical equation and the delta H is given. Average bond enthalpies are shown in the table. So bond enthalpies are given for OH bond, O double bond O and HF. Question. What's meant by the term average bond enthalpy? In rough language for understanding, bond enthalpy is the amount of energy required to break a bond. But when it comes to definition, in order that it can be compared, we should also specify that bond enthalpy is the amount of energy required to break 1 mole of a specific bond in 1 mole of the molecules in gaseous state. Otherwise, the energy required to break a same bond in the solid state of the compound and in the liquid state of the compound will be different from the amount of energy required to break it if it is in the gaseous state. So the definition goes like this. Average bond enthalpy is the energy required to break 1 mole of a bond in 1 mole of the gaseous molecules. Part 2. Calculate the bond enthalpy of the fluorine-fluorine bond. So I have written here the equation given in the question once again along with the delta H value. The delta H for any reaction is the amount of energy taken in to break the bonds minus the amount of energy released while the bonds are made. So we could write this as delta H is equal to energy taken in when the bonds are broken minus energy released when the bonds are made. By completing this equation, we can find out the fluorine-fluorine bond enthalpy. So let's write minus 598 equals the energy taken in when the bonds are broken is 2F2, which is the mystery thing that we have to calculate, and then 2 times 2H2O. There are 2 OH bonds in every molecule of H2O. Therefore, it will be 2 times of 2 times 1 OH bond, which is 464. That is now used to subtract the other one. Bonds are made. Oxygen, it is 498. Then minus 4 times of hydrogen fluoride. Each one is 568. That simplifies to minus 598 is equal to 2F2 plus 4 times 464 is 1856 minus 498 minus 4 times of 568 is, putting into the calculator, 2272. Therefore, rearranging, 2F2 is equal to minus 598 minus 1856 plus 498 plus 2272, which simplifies to 316. Therefore, one fluorine-fluorine bond enthalpy will be 316 division 2, which is equal to plus 158 kilojoules per mole. Question 17. This question is about reaction rates. Aqueous iron 3 ions, Fe3 positive aqueous, react with aqueous iodide ions I minus aqueous as shown below. So there is a redox reaction equation given there. You can see that Fe3 positive ions are reduced to Fe2 positive and iodide ions are oxidized to iodine. A student carries out 3 experiments to investigate how different concentrations of Fe3 positive aqueous and iodide aqueous affect the initial rate of this reaction. The results are shown below. So 3 experiments with different concentrations of the reactants and the respective initial rates are given in the table. Question: determine the rate constant and a possible 2-step mechanism for this reaction that are consistent with these results. So let us start by writing the general rate equation. Rate is equal to the rate constant times concentration of the reactants Fe3 positive. We need to put an exponent here, but we do not know the order of the reaction with respect to Fe3 positive yet. Therefore, let's keep it blank. Then this is multiplied by iodide ions. Again, we need to find out the order of the reaction with respect to iodide, and then we have to fill it up. Looking into the first and second experiment, we can see that the concentration of Fe3 positive is doubled, whereas the concentration of iodide ions has been kept the same. Let's say times 1. And then let's look at what happens to the initial rate here. So in order to exactly find out how many times the initial rate has changed, it's better to divide 1.62 times 10 to the power of minus 3 by 8.10 times 10 to the power of minus 4. Putting into this calculator, we get 2. That means this is multiplied by 2. So we can now say that when the Fe3 positive concentration is changed by 2, the rate also gets changed by 2, a factor of 2 itself. Therefore, it is proportional. Hence, the order of the reaction with respect to Fe3 positive is 1. Now looking into the experiments 1 and 3, the concentration of Fe3 positive is kept constant here, whereas the concentration of iodide ions has doubled. This is multiplied by 2. Okay. Now what happened to the initial rate? In order to find out how many times has the initial rate changed, if at all, what we do is we put 3.24 times 10 to the power of minus 3 over 8.10 times 10 to the power of minus 4, and putting into that calculator we get 4. That means when the concentration of iodide ions changes by 2, then the initial rate changes by 4, which means the order of the reaction with respect to iodide ions is 2. Having found the order of the reactions, we can now use this equation to find the rate constant. So let's put rate, which is given here for the first experiment, 8.10 times 10 to the power of minus 4 is equal to K, which we don't know, but we know the concentration of Fe3 positive here for the first experiment, 4.00 times 10 to the power of minus 2 to the power of 1 multiplied by concentration of iodide, 3.00 times 10 to the power of minus 2 to the power of 2. Making K the subject, K equals 8.10 times 10 to the power of minus 4 in the numerator divided by 4.00 times 10 to the power of minus 2 to the power of 1 times 3.00 times 10 to the power of minus 2 to the power of 2. Putting this in the calculator we get 22.5. Now we have to work out the units. The unit for the initial rate is moles per dm cubed per second. So let's put that in the numerator. So for units, moles per dm cubed per second in the numerator divided by the concentration, that is moles per dm cubed to the power of 1 times moles per dm cubed to the power of 2, which essentially is moles per dm cubed per second divided by, let's break this out, moles to the power of 1 and this 2 is 3. So moles to the power of 3 dm cubed, which will be minus 3 to the power of 3, which is minus 9. This will simplify to mole square in the denominator. Therefore, let's write 1 times per second in the numerator. In the denominator is mole square dm to the power of minus 6. Bringing them to the numerator, we can now write moles with the power of minus 2 dm to the power of 6 seconds to the power of minus 1. So that will be the unit here. Moles to the power of minus 2 dm to the power of 6 per second. Now we have to identify the two-step mechanism for this reaction. So there will be one slow reaction first, and then there will be a fast step of the reaction second, and ultimately please take care that the result of the overall reaction does not change. In the first step, we could say that Fe3 positive will react with two iodide ions to form an unstable intermediary, which will then react with the remaining Fe3 positive ion to form the final products. So let's write here slow step wherein Fe3 positive aqueous reacts with two iodide ions aqueous, giving an unstable intermediary Fe(I2) with a positive charge aqueous. This intermediary then will react with Fe3 positive ions giving the final 2 Fe 2 positive aqueous plus iodine aqueous, and make sure that it is balanced, and we will write this is slow step and this is fast step. It is balanced. Alright. Part B. A student carries out an investigation to find the activation energy EA and the pre-exponential factor A of a reaction. The student determines the rate constant K at different temperatures T. The student then plots a graph of ln K against 1 over T as shown below. Okay, so therefore the graph is plotted here. Let's look at the question. Draw a best fit straight line and calculate the activation energy in joules per mole. Give your answer to 3 significant figures and show your working. So you can draw a line of best fit using your ruler. Now a little bit on the activation energy. It all starts from the Arrhenius equation. The Arrhenius equation goes like this: K equals A e to the power of minus EA over RT. It consists of 2 parts. This is called the pre-exponential factor. And this part is called the exponential factor. If we take ln on both sides, we get ln K is equal to ln A. I can put all of them in the bracket first. E to the power of minus EA over RT. Going by the A-level mathematics that you learned in AS level, going by the logarithmic rules there, you can see ln K is equal to ln A plus ln e to the power of minus EA over RT. Right? Now this ln and the e will cancel out each other, and therefore it will simplify to ln A minus EA over R times 1 over T. So this forms an equation in the form of y is equal to mx plus c, where this gradient is negative here. Okay. So that is EA over R is the gradient, x is the one which we are plotting on the x-axis, and ln K on the y-axis. So if you imagine the curve, the graph that we have seen in the question, ln K is here along the y-axis, 1 over T along the x-axis, and we have got a line which is going down like this because its slope is negative, and therefore here m is equal to minus EA over R. Okay, the point at which it will meet the y-axis is ln A, from which we can calculate the pre-exponential factor. Therefore, in order to find the activation energy, let's say minus EA over R, which is the gradient of the line, that should be equal to the m, where it will be y2 minus y1 over x2 minus x1. Now let's work out the y2 and y1 on the graph that we have just drawn the line. So on the y-axis, 1 is divided into 10 divisions, therefore each division is 0.1. So if I take this point, its y coordinate is going to be 27.7, and this y coordinate is going to be 29.3. The respective x coordinates are, this is 4.50 and this is 2.50. Let us take this point as P2 and this as P1. So we will be putting in y2 minus y1 over x2 minus x1. Putting in the plotted values, 27.7 minus 29.3 all over 4.5 minus 2.5. Here we need to remember there is a multiplication by 10 to the power of minus 3, which you would have noticed on the x-axis. 10 to the power of minus 3. That is a very common student error not to recognize this. Putting into the calculator, this gives me minus 800, which means minus EA over R is equal to minus 800. Therefore, EA will be equal to 800 times the gas constant R. That is equal to 800 times 8.314, which gives us 6651.2. We can write this as 6651 joules per mole. To calculate the value of A, the pre-exponential factor, I need to extend this line to meet the y-axis. So using a ruler to extend this, okay, it meets somewhere here. So going by these divisions, it is 31.4. So we could write here from the graph A equals ln A equals 31.4, which means A equals, you know, the ln has got a base E here. When I make A the subject, E will go to the other side and this will become the power. Putting into the calculator, this gives 4.333 times 10 to the power of 13. So we could write here 4.33 times 10 to the power of 13. Question 18. Nitrogen monoxide NO and oxygen react to form nitrogen dioxide in the reversible reaction shown in equilibrium 18.1. 2NO gaseous plus O2 gaseous gives 2NO2 gaseous. Question. Write an expression for Kc in this equilibrium and state the units. The expression for Kc for this reaction is concentration of NO2 to the power of 2 in the numerator divided by concentration of NO to the power of 2 times concentration of O2 to the power of 1 in the denominator. To derive the units for Kc, let us write the units in the numerator and denominator. The numerator is concentration of NO2 to the power of 2. So it will be moles per dm cubed to the power of 2. In the denominator also, moles per dm cubed to the power of 2 times moles per dm cubed. These two equal quantities cancel out, and therefore we have moles per dm cubed in the denominator, which when comes to the numerator becomes per mole dm cubed. Part B. A chemist mixes together nitrogen and oxygen and pressurizes the gases so that their total gas volume is 4 dm cubed. The mixture is allowed to reach equilibrium at constant temperature and volume. The equilibrium mixture contains 0.4 moles NO and 0.8 moles O2. Under these conditions, the numerical value of Kc is 45. Calculate the amount in moles of NO2 in the equilibrium mixture. The question provides us with the number of moles of NO and oxygen at equilibrium, and that's what matters in these calculations. So let's write at equilibrium number of moles. Okay, first let's write nitrogen oxide, O2 and NO2, which we need to calculate now. Let's put a question mark. In the case of NO, it is 0.40 moles, and oxygen is 0.80 moles. Okay, now we need to figure out the concentration from this, so we need volume. So volume is equal to 4 dm cubed. Same here and here also. Right, therefore concentration equals concentration at equilibrium. Equals, so we will have number of moles divided by volume. So 0.4 divided by 4 is equal to 0.1. 0.8 divided by 4 is equal to 0.2, and in the other case we have to calculate it. So rewriting the equation for Kc, 45 equals concentration of NO2 to the power of 2 divided by concentration of NO to the power of 2 times concentration of oxygen to the power of 1, which is, we do not know the numerator, so let's keep it like that. In the denominator, concentration of NO is given to us, we calculated it, so therefore NO is 0.1 square times concentration of oxygen is 0.2 to the power of 1. So rewriting this, NO2 concentration to the power of 2 is equal to 45 times 0.1 square times 0.2, which gives us from the calculator 0.09. that is NO2 concentration square. Therefore NO2 concentration is equal to square root of 0.09 leading to 0.3 moles per dm cubed. Therefore number of moles of NO2 at equilibrium is equal to 0.3 times 4 is equal to 1.2 moles. 1.2 moles. Part C. The values of Kp for equilibrium 18.1 at 298 Kelvin and 1000 Kelvin are shown below. 2 NO gaseous plus O2 gaseous reversible reaction gives 2 NO2 gaseous. Then the table showing the temperature and the Kp per atmosphere are also shown. Question. Predict with a reason whether the forward reaction is exothermic or endothermic. Here we are talking about Kp, and in the earlier part of the question we were talking about Kc. Both are similar expressions. The difference is Kp applies to gas phase reactions, and while Kc is calculated using the molar concentrations of the products and the reactants at equilibrium, Kp uses partial pressures. These are the two expressions for Kc and Kp, and you can see that they behave in the similar way. Only thing is, one is in molar concentrations and the other is in partial pressures. Now let us look at what the question is asking. We need to figure out what's the nature of the forward reaction. Now let's look at the table. When the temperature increases from 298 Kelvin to 1000 Kelvin, we can see that the Kp decreases. This indicates that when the temperature is increased, the equilibrium shifts to the left. So going by the Le-Chatelier principle, the backward reaction must be endothermic. Therefore, the forward reaction is exothermic. So the forward reaction is exothermic, and we also should state the reason for our conclusion as Kp decreases as temperature increases. Part 2. The chemist increases the pressure of the equilibrium mixture at the same temperature. So he increases the pressure only, temperature is kept constant. State and explain in terms of Kp how you would expect the equilibrium position to change. By saying the pressure of the equilibrium mixture is increased, it means the total pressure is increased. The partial pressure is calculated based on the mole fractions times the total pressure, and you can see that the denominator, which represents the number of moles of the reactants, is more than the numerator. Therefore, when you calculate the partial pressure product of the reactants based on the total pressure, initially the Kp will decrease because the denominator will increase. But then, going by the Le-Chatelier principle, what will happen eventually is the system will correct itself. It will start producing more of the products by shifting the equilibrium to the right, and then Kp will be restored. So this is what we need to bring in our answer. So we should write as total pressure is increased, initially Kp will decrease. But eventually the equilibrium will shift to the right, Why does it shift to the right? As there are more number of moles on the product side. More number of moles actually on the reactant side. Okay, and then what will happen? But eventually the equilibrium will shift to the right and Kp ratio will be restored. Making it stay the same. So in our answer we have brought in what will happen when the total pressure is increased. We have also brought in what will happen to the equilibrium position. We said it will shift to the right. Eventually more products will be formed as there are fewer number of moles on the product side than on the reactant side, and hence Kp ratio will be restored, making it stay the same. That is actually 3 marks. Question 19. This question is about acids and bases found in the home. Ethanoic acid CH3COOH is the acid present in vinegar. A student carries out an experiment to determine the pKa value of ethanoic acid. The concentration of ethanoic acid in the vinegar is 0.870 moles per dm cubed and the pH of the vinegar is 2.41. Question. Write the expression for the acid dissociation constant Ka of ethanoic acid. Ka is the acid dissociation constant. It's a measure of how much does the acid dissociate when dissolved in water. When a weak acid like ethanoic acid is dissolved in water, it partially breaks down to form hydrogen ions and its conjugate base, and it reaches a state of dynamic equilibrium. And at that point we can write Ka is equal to the product of the concentration of hydrogen ions and the concentration of the conjugate base of ethanoic acid, which is CH3COO minus 2 the concentration of CH3COOH. Part 2. Calculate the pKa value of CH3COOH. Give your answer to 2 decimal places. Look at what information we have. We have the concentration of ethanoic acid and we also have the pH of the solution. Working backwards, let us write what pKa is. pKa, just the same way as pH, is equal to minus log to the base 10 of Ka value. We should also remember that for a weak acid, the concentration of hydrogen ions is equal to the concentration of its conjugate base, that is CH3COO minus, at equilibrium. Therefore, H positive concentration is equal to CH3COO minus, which actually reduces the Ka equation to H positive square over concentration of the acid CH3COOH. So the strategy for this question is we will find hydrogen ion concentration from the pH value that's given to us. We already know the concentration of the acid. From that we can find the Ka, and from there we can find pKa. We know pH is equal to minus log to the base 10 of hydrogen ion concentration. Mathematically this is equal to log to the base 10 of hydrogen ion concentration to the power of minus 1. Therefore, hydrogen ion concentration to the power of minus 1 is equal to 10 to the power of pH, which leads to hydrogen ion concentration is equal to 10 to the power of minus pH. So if we know the pH is equal to 2.41 here, we can write hydrogen ion concentration is equal to 10 to the power of minus 2.41. Okay. You don't need to remember all these steps. I just explained how pH gets converted into hydrogen ion concentration mathematically. Putting into the calculator, we get this value as 3.89 times 10 to the power of minus 3 moles per dm cubed. Therefore, Ka equals, in the numerator we have 3.89 times 10 to the power of minus 3 to the power of 2 divided by the concentration of the acid, which was given as 0.870. That gives a value for Ka as 1.7393 times 10 to the power of minus 5. Therefore, pKa equals minus log to the base 10 of whatever we obtained here, 1.7393 times 10 to the power of minus 5, and putting into the calculator we get it as 4.76. You need to just remember hydrogen ion concentration is equal to 10 to the power of minus pH. So this is just the mathematical derivation of it. Part 3. Determine the percentage dissociation of ethanoic acid in the vinegar. Give your answer to 3 significant figures. Percentage dissociation of the acid means how much hydrogen ion concentration does it produce if the concentration of the acid were 100 moles per dm cubed. Therefore, we could write percentage dissociation is equal to hydrogen ion concentration out of the acid concentration times 100 written as a percentage, which is equal to 10 to the power of minus 2.41, which was the pH, divided by the concentration of the acid 0.870 times 100. That gives us to 3 significant figures, 0.447%. Part B. Many solid drain cleaners are based on sodium hydroxide NaOH. A student dissolves 1.26 grams of a drain cleaner in water and makes up the solution to 100 cubic centimeters. The student measures the pH of this solution as 13.48. Determine the percentage by mass of NaOH in the drain cleaner? Give your answer to 3 significant figures. Before starting to answer this question, a small discussion on how we calculate the pH of an alkali such as NaOH. When NaOH dissolves in water, it can't dissociate to produce any hydrogen ions, right? Therefore, we assume that all the hydrogen ions come from the dissociation of water. So if we write the dissociation constant for water, let's say Ka, that is equal to hydrogen ion concentration coming from water times OH ions divided by the concentration of water. By definition, concentration of water is taken as 1. So we can rewrite this as Ka becomes a new constant Kw equals hydrogen ion concentration times OH ion concentration. When NaOH dissolves in water, it's assumed that all the hydroxide ions come from NaOH. So that's equal to the concentration of NaOH. The value of Kw will be provided in your data sheet as 1 times 10 to the power of minus 14. Therefore, we can write 1 times 10 to the power of minus 14 is equal to hydrogen ion concentration times the OH ion concentration, which means 1 times 10 to the power of minus 14 is equal to, just as we discussed in the previous part of the question, hydrogen ion concentration can be derived from the pH value as 10 to the power of minus pH, which is 13.48 here, times the concentration of OH ions. Rewriting this, hydroxide ion concentration, which is the same as concentration of NaOH, is equal to 1 times 10 to the power of minus 14 divided by 10 to the power of minus 13.48, and that gives us 0.302 moles per dm cubed. This actually means there are 0.302 moles of NaOH in 1 liter, but we are talking about 100 ml. Therefore, in 100 ml, the number of moles will be 0.0302 moles. Therefore, mass of NaOH in 100 ml of the cleaner solution is equal to 0.0302 times the relative formula mass of NaOH, that is 40, and that gives us 1.21 g. And therefore, to calculate the percentage by mass of NaOH in 1.26 grams of the solid, we put 1.2 in the numerator, 1.21 in the numerator and 1.26 in the denominator times by 100 and written as a percentage. That gives us 95.9 percentage. So the answer for this is 95.9 percentage. Part C. Sodium carbonate Na2CO3 is a base used in washing soda. Na2CO3 contains the carbonate ion CO3 2- as shown below. Draw the dot and cross diagram for the carbonate ion. Show outer electrons only and use different symbols for electrons from carbon and oxygen and any extra electrons. Looking at the diagram of the carbonate ion here, we can see that there will be 2 bonding pairs here, 1 bonding pair here, 1 bonding pair here, and there will be extra electron on this oxygen and on this oxygen atom. So let us draw the carbon atom at the center. One oxygen atom here, one oxygen atom here, and one more oxygen atom here. And before we forget, let us put the square bracket here and square bracket here and put the overall charge as 2 minus here. So labeling this as carbon, oxygen, oxygen, oxygen. Going by this, there should be 2 bonding pairs here on the oxygen atom. Let's use the dot from the oxygen and a cross from the carbon, one more dot from the oxygen and one more cross from the carbon. As oxygen has got 6 electrons on the outer, let us draw the remaining 4 here. 2, 3 and 4. Same is the case here as well. 1, 2, 3, 4 and 5, because only one dot is used from the oxygen here, one cross from the carbon, one dot from the oxygen here and one cross from the carbon. 1, 2, 3, 4 and 5. These 2 oxygen atoms have an extra negative charge on them, so we should mark one extra electron here and here and label this as extra electron. Extra electron here also, and check whether everything is all right. Carbon has got 1, 2, 3, 4 crosses, and this oxygen has got 1, 2, 3, 4, 5, 6 dots, and this oxygen has got 1, 2, 3, 4, 5, 6 dots. Perfect. And here 1, 2, 3, 4, 5, 6 and one extra electron there, one extra electron there. Perfect. Question 20. This question is about the halogen group of elements and some of their compounds. The halogens show trends in their properties down the group. The boiling points of 3 halogens are shown below: chlorine, bromine, iodine, and their respective boiling points, and they show an increasing trend. Question. Explain why the halogens show this trend in boiling points. Whenever we talk about boiling points or melting points, we should discuss the intermolecular forces and not the internal forces. Chlorine, bromine, iodine are elements going down the halogen group. When you go down the group, the number of shells increases, and therefore the number of electrons increases, and therefore the size of the atom increases, and therefore there will be increased intermolecular forces. So we write down the group the number of electronic shells increases, the number of electrons increases, and this leads to greater London forces. Of intermolecular attraction. If you want, you can even underline this to make it conspicuous. Intermolecular attraction. Hence, greater amounts of energy is required to overcome these intermolecular forces of attraction resulting in higher, we are talking about boiling points here, so write higher boiling points. Part B. Hydrogen iodide, HI, is decomposed by heat into its elements. 2HI gaseous gives H2 gaseous plus I2 gaseous. Delta H is plus 9.5 kJ per mole. The decomposition is much faster in the presence of a platinum catalyst. Complete the enthalpy profile diagram for this reaction using formulae for the reactants and products. Use EA to label the activation energy without a catalyst. Use EC to label the activation energy with a catalyst, and use delta H to label the enthalpy change of reaction. This is an easy 3-mark question. First of all, make sure that this is endothermic or exothermic. Delta H is positive, therefore it is endothermic. Therefore, the reactants must be at a lower energy level and the products will be at a higher energy level. In order to react, the reactant molecules should reach a higher energy level, that is the activation energy. Let's say this is the activation energy. From there, when the reaction happens, they end up at this product energy level. So let's write this as 2HI gaseous at this energy level, and this is H2 gaseous plus iodine gaseous. Alright, therefore the activation energy will be the difference of energy level between the reactant and the point at which the reaction takes place. Let's classify this as EA. When the catalyst is used, the activation energy required is reduced. Let's mark this as a lower level, and therefore at this point the new activation energy, which is a lower one, should be classified as EC. Now delta H is the difference in the energy levels between the reactants and the products. Therefore we can classify this difference as delta H, which is given to be equal to plus 9.5 kJ per mole. Part C. Compound A is an oxide of chlorine that is a liquid at room temperature and pressure and has a boiling point of 83 degrees centigrade. When 0.4485 grams of A is heated to 100 degrees centigrade at 1.00 times 10 to the power of 5 pascals, 76 centimeter cubed of gas is produced. Determine the molecular formula of compound A and show all your working. At 100 degrees centigrade, A is given to become a gas, and we have also been given pressure, volume as well as temperature. Therefore, we need to use PV is equal to nRT, the ideal gas equation for this. So let's write the formula. PV is equal to N times RT. Let's fill in all the details which are available from the question. Pressure is 1 times 10 to the power of 5 times volume is 76 cubic centimeters, which we need to convert into cubic meters. Therefore, it's 76 times 10 to the power of minus 6 equals N, which we don't know. R we know is the gas constant, which is 8.31 times temperature. We need to add 100 degrees to 273, therefore it is 373. That gives N equal to 10 to the power of 5 times 76 times 10 to the power of minus 6 divided by 8.31 times 373. That gives us 2.45 from the calculator, 19 times 10 to the power of minus 3 moles. We are after this molecular formula, therefore let's calculate the mass first, which can be obtained from the number of moles and the number of grams. We know number of moles is equal to mass in grams divided by molecular mass. Therefore, MR should be equal to G divided by En, and the grams is here 0.4485 divided by the number of moles we just calculated, 2.4519 times 10 to the power of minus 3, and that gives us 182.91, approximates to 183. So from here on, it's only a trial and error method because we have only been told that it is an oxide of chlorine. So oxide of chlorine means it could be Cl with X atoms and O with Y number of atoms. Therefore, Cl is 35.5 times X plus 16 for oxygen times Y totals 183. By trial and error and by spending a minute or two, we can get this as Cl2 oxygen 7. So the molecular formula of compound A is Cl2O7. Part D. It's a long worded question, and therefore while reading, let's keep on underlining the important information bits. Compound B is an iodate 5 salt of group 1 metal. The iodate 5 ion has the formula IO3-. A student carries out a titration to find the formula of compound B. The student dissolves 1.55 grams of B in water and makes up the solution to 250 cubic centimeters in a volumetric flask. The student pipettes 25 cubic centimeters of this solution into a conical flask, followed by 10 cubic centimeters of dilute sulfuric acid and an excess of potassium iodide aqueous. The iodate 5 ions are reduced to iodine as shown below. Step 3. The resulting mixture is titrated with 0.150 moles per dm cubed sodium thiosulfate. Okay, the equation is also given here. The student repeats step 2 and step 3 until concordant titers are obtained. Okay, so this is the famous sodium thiosulfate titration question, very popular question. Let's read part 1. Complete table 20.1 and calculate the mean titer that the student should use for analyzing the results. So let's calculate the titer for each experiment. So this is 24.00. That's a trial one. The next one is 23.40, and the next one is 23.75, and the last one is 5, 10 minus 2, 8, and 23. We will take these two into consideration because they are the concordant results. Therefore, mean will be 23.75 add 23.85 47.60 divided by 2, that gives us 23.80. That's a quick 2-mark question for us. The uncertainty in each burette reading is plus or minus 0.05 cubic centimeters. Calculate the percentage uncertainty in the titer obtained from titration 1. Give your answer to 2 decimal places. The formula for the percentage uncertainty is uncertainty multiplied by the number of readings. Whole divided by the actual reading multiplied by 100 written as a percentage. So that's equal to, in this case, the uncertainty is 0.05 times the number of readings is 2 divided by the actual reading for titration 1 is 23.40 times 100, and that gives us 0.4273. To 2 decimal places it is 0.43. Next part of the question. Describe and explain how the student should determine the end point of this titration accurately. Here we should explain what indicator to add, when to add, and what will be the color change for the solution. If you look at what happens during the titration here, we have thiosulfate in the burette and iodine solution in the conical flask. So this is iodine solution with water, and this is S2O3 2 minus. Alright, now what happens is, when we are titrating it, we need to identify when the entire iodine in the solution is reacted with this sodium thiosulfate. Now if we add starch at the beginning itself, what will happen is iodine will bind strongly with the starch, and therefore even after the iodine is completely reacted with thiosulfate, that blue-black color of the iodine will still remain. Therefore we should remember to add starch only at the near the end point. So when this titration happens, at the end of it there will be a kind of yellow color to this solution, which is an indicator that almost all of the iodine is now reacted. At that point we need to add starch, and then immediately the remaining small part of the iodine will make it blue-black. A few more drops of thiosulfate will react with those iodine particles also, and it will make the solution colorless. During titration, add starch near the end point shown by yellowish solution indicating low concentration of iodine. The starch will turn the color to blue-black, when the remaining iodine also is completely reacted. The solution will change from blue-black to colorless. Note the final reading. At this end point. So let's read this once again. During titration, add starch near the end point shown by yellowish solution indicating low concentration of iodine. The starch will turn the color to blue-black. When the remaining iodine also is completely reacted, the solution will change from blue-black to colorless. Note the final reading at this end point. Fine. Determine the relative formula mass and formula of the group 1 iodate B. Show your working. So let's start by working out the number of thiosulfate moles that took part in the titration. Therefore, N bracket S2O3 2 minus in the titration reaction will be 23.8 divided by 1000 to convert that into dm cubed times 0.150, that's equal to 3.57 times 10 to the power of minus 3 moles. This comes from volume times concentration. From this reaction equation, we know that the ratio of thiosulfate to iodine is 2:1. Therefore, number of iodine moles reacted will be half of 3.57 times 10 to the power of minus 3 moles. From the calculator we get it as 1.785 times 10 to the power of minus 3 moles. These iodine moles have come from the first equation, and therefore from that equation we can find out the number of moles of iodate ions, and here the ratio is 3:1. Therefore the number of iodate ions is equal to whatever we got here, 1.785 times 10 to the power of minus 3 multiplied by 1/3. That gives us 5.95 times 10 to the power of minus 4 moles. These were in 25 cubic centimeters of the solution. Hence, number of iodate moles in 250 cubic centimeters will be 10 times of this, that is equal to 5.95 times 10 to the power of minus 4 times a 10 will make it to the power of minus 3. This comes from how many grams of the salt? 1.55 g of the iodate salt. We know number of moles is equal to mass in grams divided by the MR. Therefore, MR of the substance should be equal to mass in grams divided by the number of moles. Mass in grams is what? 1.55 divided by number of moles is equal to 5.95 times 10 to the power of minus 3, and that gives us 260.5 from the calculator. This is so many grams per mole. The question had asked the relative formula mass of the compound, therefore we have answered one part of the question now. So we have been told that this is an iodate salt of the group 1 metal. So let's write this format: some group 1 metal, then this iodine which has got oxidation state of 5, and therefore we have got this O3 also, and this is the iodate salt, right? This has got a molecular mass of 260.5. Since we know the AR of iodine 126.9 and the AR of oxygen, which is 16 times 3 of them here, we can easily calculate the AR of the mystery element here, X. Hence AR of X is equal to 260.5 take away 126.9, add 16 times 3, and putting into the calculator we get this as 84.73 approximating to 85. Now let's look at the periodic table. Which element has got this atomic mass? It's the rubidium. Therefore, relative formula mass of compound B is 260.50 g per mole, and the formula of B is RbIO3. Question 21. This question is about some reactions of D block elements and their ions. Table shows standard electrode potentials which will be needed within this question. We have been provided with several redox reactions along with their respective electrode potentials. Part A complete the electron configuration of a nickel atom. We know the atomic number of nickel is 28. And fortunately, nickel does not belong to those two elements which are showing anomaly in their electron configuration in the D series. And they are copper and chromium. In the case of nickel, we can straight away start filling in the electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 3d, and then pause there. Before the 3d10 is completely filled in, 4s2 will get filled in. Therefore, we will only require 8 here. Now, electron configuration of a nickel 2 positive ion. In the case of nickel 2 positive ion, what it means is it has lost 2 electrons. And the 2 electrons will go away from the 4s2. Therefore, the remaining will be 2s2, 2p6, 3s2, 3p6, and 3d8. Part B. A standard cell is set up in the lab with the cell reaction shown below. Nickel solid plus iodine aqueous gives nickel 2 positive ion aqueous plus 2 iodide ion aqueous. Draw a labeled diagram to show how this cell could be set up to measure the standard cell potential. Include details of apparatus, solutions, and standard conditions required. So we need to draw the 2 half cells, the salt bridge, the electrodes, the voltmeter in the solution containing the ions, as well as describe what standard conditions are required. First and foremost, we should determine which half cell will be on the left and which one will be on the right. Therefore, let's look at this nickel and iodine systems. Let us shortlist these 2 reaction systems. Looking at them, we can see that the nickel system has got more negative electrode potential. Therefore, we need to rewrite this equation as an oxidation reaction. Currently, it's written as a reduction reaction. Also, we need to draw the nickel system on the left when in the diagram, because nickel solid will undergo the oxidation. The reaction equations will be nickel solid will get oxidized to nickel 2 positive ions aqueous plus 2 electrons, and then iodine aqueous plus 2 electrons will become 2 iodide aqueous. So drawing the 2 half cells, okay, so this will be having the nickel electrode, and this will be having another electrode. We should determine which one it should be, because iodine and iodide aqueous need an electrode here. So it should be a platinum electrode which will not react with them. And this is nickel solid. Okay, and this in this solution we will have nickel 2 positive ions here, and we will have iodine aqueous as well as iodide aqueous. Okay, and there should be very important, there should be a salt bridge between them so that the ions can go from one cell to the other. This should be connected by a wire having a voltmeter there to measure. Okay, so we will label them now. Salt bridge. Then to mention the standard solution, 1 mole per dm cubed, that's the concentration, and the temperature should be 298 degrees Kelvin. So we have mentioned platinum, nickel. All right, so let's write here the standard conditions. 1 mole per dm cubed, 298 Kelvin temperature. This is solution. Okay. Predict the standard cell potential of this cell. This is 0.54 minus of minus 0.25, and that gives us 0.79 volts. Part C. Use the information in the table to help you answer both parts of this question. Write the overall equation for the oxidation of Fe2 positive by acidified H2O2. So let's look for the two reactions mentioned in the question. So one is the oxidation of Fe2 positive, so that's this one, and by H2O2 acidified, that is this one. Now comparing the electrode potentials of these two reactions, you can see that the electrode potential for oxidation of Fe2 positive should be less positive than the 1.78 volts here. Therefore, we need to rewrite this equation by reversing it and showing it as an oxidation reaction. Currently, it's written as a reduction reaction. Also, we need to multiply this equation by 2 to balance the species, also the number of electrons. Adding them together, we will get the overall reaction. Writing the overall equation, 2Fe2 positive aqueous plus H2O2 aqueous plus 2 hydrogen ions aqueous gives 2Fe3 positive aqueous plus 2H2O liquid. Next part of the question. Zinc reacts with acidified Cr2O7 2- ions to form Cr2 positive ions in two stages. Explain why this happens in terms of electrode potentials and the equilibria. Include overall equations for the reactions which occur. Now let us look at all the reaction systems that may be involved as per the question. So zinc is reacting with Cr2O7 2-, which produces Cr3 positive here, and then we end up with the Cr2 positive aqueous. Therefore, these three reaction systems are involved. Starting from zinc reacting with Cr2O7 2-, we can see that the electrode potential here minus 0.76 volts is more negative than that of 1.33 volts. Therefore, we need to reverse this reaction equation and write it as an oxidation reaction. Currently, it is a reduction reaction. Also, we need to see that this is 2 electrons here and this is 6 electrons here. Therefore, I need to multiply this by 3 and then reverse this and write this as a forward reaction, the second reaction. And therefore, we will be able to get the overall first stage reaction. So, writing them after multiplying the first equation by 3, we get 3Zn solid plus Cr2 O7 2- aqueous plus 14 hydrogen ions aqueous, they give 3Zn 2 positive aqueous plus 2Cr 3 positive aqueous plus 7 H2O, which is liquid. This is the first stage of the reaction. From this Cr3 positive, we need to get Cr2 positive ions. And therefore, let's go back to the table and see which reaction might be useful. After the first stage, we have the Cr3 positive aqueous ions on hand now. Now they have to be converted into Cr2 positive aqueous. Looking into the various reaction systems here, you can see that the electrode potential of zinc system is more negative than this. Therefore, zinc solid can reduce Cr3 positive to Cr2 positive. Just as earlier, we need to reverse this reaction and write it as an oxidation reaction and also multiply this by 2 to balance the two equations. Therefore, Zn solid plus Cr3 positive multiplying by 2 aqueous gives Zn positive 2 positive aqueous plus 2Cr 2 positive, which is the end product that we wanted here, aqueous. We also need to write the reason here. So we can write this happens because the electrode potential of Zn is more negative than that of Cr3 positive. 3 different reactions of copper compounds are described below: reaction 1, reaction 2, and reaction 3. Let us look at the overall task for us in the question. Identify compounds C to F by the formulae or structures as appropriate, and include equations, any changes in the oxidation number and working. So let's look at the reaction 1. Aqueous copper 2 sulfate reacts with excess aqueous ammonia in a ligand substitution reaction. A deep blue solution is formed containing an octahedral complex ion C, which is a trans isomer. So we need to identify C from this, write the equation, and then also draw the trans isomer shape. The complex ion in aqueous copper sulfate is CuH2O6 times 2 positive. When excess ammonia reacts with this complex ion in a ligand substitution reaction, ammonia replaces 4 H2O molecules. Therefore, it forms CuH2O2 NH3 4 times, and the same 2 positive charge remains, plus some water molecules. Will balance it now. To balance this, we have to put 4 NH3 here and 4 H2O here. This is a deep blue complex ion. Chemistry students may naturally have a question: why does it stop at replacing only 4 water molecules? Why doesn't NH3 form 6 ligands here? In fact, the substitution stops after replacing 4 water molecules due to a phenomenon in which the copper ion experiences some geometric distortion. But that is beyond the specifications for A-level OCR chemistry, and you will be learning this when you go to undergraduate course in chemistry. So to answer this question, we have written the equation already. Let us very clearly say C is identified as CuH2O twice NH3 4 times, forming a complex ion with 2 positive charge here. So that part is done. Now we need to draw the trans isomer shape. Trans isomer diagram. Let us put copper at the center and then mark H2O here. H2O here, and then draw the 4 wedges and dashes, dash here. So this is NH3, NH3, another NH3, and the 4th NH3, and then darken this. Now put the square brackets and mark 2 positive charge here. The 2 H2O molecules on either side here represent that it is a trans isomer. Reaction 2. Copper 1 oxide reacts with hot dilute sulfuric acid in a disproportionation reaction. A blue solution D and a brown solid E are formed. So here we need to write the equation, identify the compounds D and E, and also show why it's a disproportionation reaction by demonstrating the changes in the oxidation number. So reaction 2. When we say copper 1 oxide, it means the copper ion in the compound has got a charge of +1 only. Therefore, it will be forming Cu2O with oxygen, aqueous, plus dilute sulfuric acid. That gives copper sulfate, aqueous, sulfuric acid also aqueous, plus it will form copper solid plus H2O. Copper sulfate aqueous is the blue solution D, and then copper is the brown solid, which is identified as E. So D and E are identified. Now let us look at the changes in the oxidation number to demonstrate why it is a disproportionation reaction. A disproportionation reaction is one in which a species undergoes both oxidation as well as reduction. Here copper has got an oxidation state of +1. It becomes 2 positive here, so it gets oxidized, and here it is 0 because it is an element and therefore it is getting reduced. Hence we can write it is a disproportionation reaction as Cu +1 undergoes oxidation to Cu2 positive and reduction to Cu0. Reaction 3. Copper 2 oxide reacts with warm dilute nitric acid in a neutralization reaction to form a blue solution. Unreacted copper 2 oxide is filtered off and the solution is left overnight in an evaporating basin. A hydrated salt F crystallizes with the percentage composition by mass. Copper, hydrogen, nitrogen, oxygen, the percentages are all given. Identify F by the formula of all the structures as appropriate. Okay. So let's write reaction 3. Copper 2 oxide means here the copper ion has got a positive charge of 2, that is Cu2 positive. Therefore, it joins with oxygen to form CuO plus 2HNO3 gives, I wrote 2HNO3 because it will form CuNO3 twice plus H2O. So here copper nitrate is the blue solution mentioned there. From this blue solution mixture, unreacted copper 2 oxide is filtered off and the solution is left overnight in an evaporating basin and hydrated salt F crystallizes. Therefore, this F must be CuNO3 twice with certain water molecules as water of crystallization. So we can write F is a hydrated salt therefore it is CuNO3 twice then some molecules of water as water crystallization. Now let's put the percentage composition of copper, hydrogen, nitrogen and oxygen here. From the question I am writing 26.29%, 2.48%, nitrogen was 11.59% and oxygen was 59.63%. These are all percentage composition by mass. Dividing these by the respective atomic mass, that is dividing by 63.5 by 1, dividing by 14, dividing by 16, we get from the calculator 0.41, 2.48, 0.82 and 3.72. Okay, now in order to find the least common ratio here, divide by 0.41. That gives us copper 1, hydrogen 6, nitrogen 2 and oxygen 9. Therefore, empirical formula of the compound is CuH6N2O9. But we already know that this is copper nitrate with X number of water molecules in it. So we need to know how many water molecules are there. Copper nitrate here and X molecules of water. Right. Now all the hydrogen will go to form the water molecules. There are 6 hydrogen here. Obviously there should be 3 molecules of water. So let us try this out. CuNO3 twice dot 3H2O. That works. All elements are balanced. Therefore we can write compound F is this one. Well, that is the end of the question paper. It's a very long one and has some questions involving quantitative calculations and also requiring deep understanding of the concepts. Hope the walkthrough was useful to you and that you thoroughly enjoyed it. If you need any clarification on any question, please feel free to post it in the comment section. I shall happily respond to it. Warm wishes, and until the next walkthrough, bye.